All right, this video is on section 12.4 through, I believe, 12.6 or 12.7. We're going to be testing the significance of the correlation coefficient. So before this, we worked with scatter plot data. We came up with the line of best fit. So for this, we're going to be testing how significant our correlation coefficient is. And our correlation coefficient is this R value. And what we want to really be testing is the population correlation coefficient. That's of everything, of all the data, and that's generally unknown because we don't have all the pieces of data. We only have a sample. So this is what's known, calculated from our sample data. So that's the R value we're going to be looking at. But when we're writing our hypothesis test, we are going to be using this Greek letter. It looks like a P, but it's pronounced rho. We are going to be checking rho to determine if the correlation coefficient of rho is close to 0 or if it's significantly different from 0. We base that off of the R value and the sample size. So we're testing if the rho equals 0. So there is no correlation, or rho doesn't equal 0. So if rho does not equal 0, that means that there is a significant correlation. So the null hypothesis, the population correlation coefficient is not significantly different from 0. So there's not a relationship, not a significant linear relationship. And the alternative hypothesis is there is a significant linear relationship because it would not be equal or closely equal to 0. It would be different than 0. And we're going to do this just like how we've done our other problems, looking at that p-value. And so we're going to be able to use the p-value using a calculator. And we could look this up using a table of values as well. And then generally we'll use the 0.05. We're not using the calculator here for the t-test. We use a different calculator. All right, so if our p-value is small, remember we reject the little guy. If the p-value is less than the significance level, 0.05, then we reject the null hypothesis. So there is sufficient evidence to conclude that there is a significant linear relationship between x and y. And if the p-value is not less than that 0.05, it tells us our data is not rare enough to reject that null hypothesis. All right, so here's some data. And we could go ahead and take that data and we could calculate an R value and our number of data pieces. And then what we're going to do is just take that into a calculator and it will give us our p-value. So for these examples, we can even do it without even having to look at the scatter plot. So let's see. My R value is 0.606501. So I'll load up my calculator. I'll go back to that number, 0.6501. Hey, John.
Have you seen Ismar?
What's that?
Have you seen Ismar?
I have not. All right, we have 12 pieces of data. And there we go. It says the p-value is 0.0002. Oh, sorry, 0.022. So the result is significant. So we do reject the null hypothesis and we say there is a significant relationship here. And I could go back and test. Let's see, where's that? Let me find some new data. So locate this Bitcoin data we looked at last time. And inside of here, there's our line of best fit and our R values. This R squared value is 0.394. Remember, that's the R squared value. I want the R value, so I'll square root 0.394, 0.627. So this has an R value of 0.627. And how many pieces of data are here? 128, or actually I think it was 129 pieces of data because this started at month 0. So 0.627. And 129. So we'll see if having a larger data changes this. So this tells us that the p-value is very low. And so this is a very rare R value to get with 129 random pieces of data. Also, if you think about it, the more pieces of data you have, if you have a lot of data that's not correlated to each other, your R value is going to be very close to 0 because those data points are going to be all over the place. But if you only have 3 data points, it's easier to have a correlation there because it's easier for those 3 to be in a line. But 129 to be kind of synced together, that's rare. So this one is significant as well. All right. So that kind of concludes that part. You just look it up, find the p-value, and decide to reject or to not reject. The next part is looking at 12.5 and 12.6 prediction and outliers. And we're going to talk about interpolation and extrapolations and outliers. Just going to move through this a little bit. So here's how we calculate our outliers with our line of best fit. So what we need to do is take the line of best fit and we add a number to it and subtract a number to it. And anything outside of that yellow line is considered an outlier. And so to get that, it has to be 2 standard deviations above or below the line of best fit. And you would have to take your residuals and calculate your standard deviation. Then you would add that and subtract it. And that would give you your outlier. And then what you could do is you could throw out some of those outlier pieces and then recalculate your line of best fit. Let's take time and all of our energy. I think we're not going to go through mathematically calculating all of those and throwing them out. But it's good for you just to notice. And, okay. So I think there is interpolation and extrapolation, which we want to talk about. To the slide for it, but we'll just look here. And I think these are topics we talked about before. Interpolation is when we make a prediction within inside of our data set. So if I wanted to predict like the exam score of 68 and what their final exam score would be, that would be an interpolation because we're inside of our data. Extrapolation would be if we took this line of best fit and went beyond the data. So if I went to like a third exam score of 90 and I could try to predict the final exam score, that would be an extrapolation because it's outside of our data. All right, that concludes chapter 12.